All right, so I always think about wavelet scattering as a kind of generalization of those convolutions, because after all, it's just some filters, and there is a research about equivariant. They try to, for example, we have an image, we want to make it invariant to translation, rotation, deformation, and for example, we want to one in MNIST data. When you rotate that, you want to be invariant, so it is still one, and therefore the research about equivariant neural network, equivariant group neural networks, but I suggest wavelet scattering rather than those research areas because first of all, you save thousands of neurons, and second of all, this has a profound background and support in harmonic analysis, and goes back to nearly 200 years ago. And but wavelet scattering is quite new because it's a kind of wavelet transform which is invariant to such deformations. And mathematicians like to break things into pieces, like the word analysis in Greek. And machine learning engineers like to learn anything, even if it is billions of parameters. They like to learn it. But neuroscientists are like in the middle. And so the question is, do we need learning for everything? Because I said last time that your ears are like filters, like wavelet transforms. So they are not learning. It's just a filter. It's a passive filter, and the weights of the filter doesn't change. And that wavelet is generalization of Fourier. There are something that generalize wavelet as well, such as shearlets. So all of these things that I just skip because they are very elementary, and we have different wavelets. For example, stick to these wavelets. You can have different scale, and you can scale it. And the one-dimensional discrete wavelet transform, you give it to low pass filter and high pass filter. This is the details. So you continue with the approximation, and again, this is approximation, this is detail, this is approximation, this is details, and finally you have a wave. You have a multi-resolute, let's say, a multi-scale data, and this is interesting because whenever you increase these things, you don't know about these things. So this is the motivation for the father, and you should. I talked about mother wavelet and father wavelet. I just skip about, and in 2D it's just the same as 1D. You have 2D, you have two frequencies, and then so everything is two-dimensional, and you have. I skip this, and you have three-dimensional as well. You can have three-dimensional as well. So, but here you have lots of parameters, and for example, you have a wavelet basis, and you want to you have some. So instead of those bases, those codes that you have in sparse coding, that you want to learn everything. Here we don't learn anything. They are fixed. There are some bases that are fixed. Deep scattering spectrum is a great article by Stephen Malott, and he proved the properties of wavelet scattering why it is useful, because it is invariant. Every image, every data is invariant to rotation, translation, deformation, and it is very easy to implement. And I use a library that they provided. It's an open source. Anybody can just use it in his Google Colab or Python code, and this is an example that you have lots of details. You can capture lots of details. And so for wavelet scattering, this is the library that I said, and also it is also embedded in PyTorch as well, so you can use it for PyTorch projects as well. And you just use, you said only I want to do scattering, and then scattering of an image, and then you have a 32 by 32 image, and you get the scattering of your image, and you get that. You calculate the scattering transform, and the size of this is like this. And I calculated that, and I noticed that it is already provided in the README. I mean, in their help. And so the default is 8 here in this formula. So this formula, if you put these parameters, you will get this using this formula. And thanks to Stefan Mallat for this great, he deserved a Nobel Prize and even more, because it is a gap between harmonic analysis and deep learning. So it's a gap between two beautiful worlds. So it combines them, and that's why the work of Stefan Mallat is very beautiful, just like the work of Geoffrey Hinton. So Stefan Mallat uses wavelet scattering, and that's why it is now very popular in Saturn, the planet that I live. It's an active research. And finally, Fourier says mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. Very beautiful. And finally, I want to quickly review frames and bases. I know it's very mathematical and many people don't like it, but I love it, especially this book, which is an introduction to frames and Rie's bases. By the way, Ries is a great, I think he's French mathematician. And so the mathematician says that we use frame theory and over complete set. It's another way of saying we use sparse coding and over complete dictionary. Of course, mathematicians tend to use fixed codes, but machine learning engineers just like to learn anything, even their own codes, because I remember Yashu Bengio said that something like we should adapt to our data, so why not learning all of those weights? And finite dimensional. So everything in finite dimension everything is easy, but it is a hard restriction that you say all of your bases are orthogonal and also orthonormal, and they provide basis which is orthogonal. It's a very hard restrictions. That's why we want to relax this restriction, and we want to just generalize it to see if it provides some benefits, and it does, because you have more flexibility to choose your function space, and so you can have many variations in your functions, and so it's better. And this frame is just the definition of a frame is that a countable sequence F1, F2, Fk is a frame if there exist constants A and B, such that if you project it, for example, this is a space, for example, a Hilbert space, although finite dimensional is trivial, but for illustration purposes, I assume you have a finite dimensional Hilbert space, and you have some bases F1, F2, and Fk, and you project your high dimensional functions. This is a function, not a vector. A function in this vector space. I mean, vector space of functions like Banach spaces, Hilbert spaces. Here we have inner product, and we use Hilbert space. And here we define the frame as these Fk that provides this relationship. So if you project it, it is bounded between a factor of norm of f squared and b factor. So it is compressed between them, and it is already satisfied in finite dimensional case because sum is finite and therefore b is finite, so it is already satisfied. And the operators, so we say that it is synthesis operator. T is a synthesis operator because we generate that. We generate that and we create some image or a text or anything. And analysis, the word analysis in Greek means break into pieces. Of course, I'm Persian, not Greek, but it has the roots in Greek literature. The word analysis, very interesting meaning. Break into pieces, break into some frames if you don't want to break it into some orthogonal bases. A frame operator is just you apply your analysis operator, so a bracket. Here you have broken that, and then you apply the synthesis operator, and then you generate this. So it goes from V to V. For example, first you apply it on your image, and so image to image. Or it depends on your data sets. For example, it could be text, it could be speech. So operators behave like the thing that we know. But for example, in terms of convolutional operators, deconvolutions, all of these things could be replaced by wavelet scattering, by the way. And tight frames, we say a frame is tight if A is B, and if we can do such thing as A is equal to B, and the partial frame is just a special case if A and B is 1. So we can do frame decomposition as you do with any as your traditional ways of decomposition, that you need some bases, some orthogonal bases, but now you have some frames, these frames, and then you decompose it. So you have some weights that says, so for example, as I said, F1, F2, F3, and you decompose it in this space. An example is, for example, one of your bases is E1, another one E1 minus 2, another one E1 plus E2. And then if you apply this S operator, you just apply the thing that I said, S. Where is that? This one. So you just apply this F and so project it into this space that has this frame basis. And so this is what you get in this example. SE1, SE2, and finally you can present your F as this. And so this is the frame decomposition.